In this video, I am going to summarize the most important concept of sampling distribution. In statistics, we deal with population and we want to study some characteristic of this population. Suppose that we focus our attention in only characteristics that we can measure with number. Quantitative variables such as height, weight, temperature, time. If we measure these characteristics in one member of the population, we can obtain the average, the mean, will be represented by mu, and also we can obtain the deviation of all measurement with respect to the mean, which will be the standard deviation. Each point in this population represents one item, one member of the population, and we can order all of these members of the population according to its corresponding measurement in a number line. If the first member of the population have this measurement, we plot this value here. If the second have this measurement, and so on, we can plot according to the measurement in that way. Members of the population that have exactly the same measurement will be stocked one above the other. If we plot all members of the population, or we organize all members of the population according to each measurement in this number line, we can obtain several shapes. But suppose that we obtain a normal distribution, which is a mound shape. This is a normal distribution. We can verify that all members stock in the center of this pile. All members have a measurement that is equal the mean of the population. For other members of the population, we can obtain its measurement according its position in this scale, will be this value. And actually, there is a deviation with respect to the mean of all measurement, and the standard deviation in a normal distribution will be a quantity similar to this, equivalent to this distance. Most of the measurement will be within 3 standard deviation, approximately 99.7% of all of them. That is the distribution for individual values. In statistics, we don't work with the entire population, but we work with sample. And we can compute the mean of the sample that will be denoted by X bar. X bar is a statistic because it's obtained from a sample. However, mu is a parameter because it's obtained from the population. But we can obtain several samples of the same size from this population, and we can compute the mean for all of them. This will be the mean for sample 1, the mean for sample 2, and so on. All of these samples have the same size n. What is a sampling distribution? The sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of the same size n. In this case, we are going to study the sampling distribution of the sample means. The samples mean are a statistic. All of these are a statistic. We want to know how are all of these values distributed. If we compute the samples mean of all possible samples of the same size, and we plot all of this value in a number line, in this distribution we are going to represent each sample by points. Then if these samples, for example, the mean is equal a specific value, we can find this value in this number line and plot this mean here. And we can do the same for the other samples. We can organize all samples according to each measurement, and we are going to stock all samples that have the same measurement one above the other. When we finish plotting all of these samples in this number line, we are going to obtain a pile like this. When we finish, we can verify that in the center of this pile we have stock all samples that have a samples mean equal exactly the mean of the population, and the shape of the distribution will be normal. Then we have a distribution for individual value here, and that is the distribution for samples mean. One important characteristic of this distribution is that the mean of all samples mean will be the mean of the population, that will be the center of the distribution, and the standard deviation of all samples mean will be the standard deviation of the population divided by a square root of n. Remember that the standard deviation of the population in this graph is equivalent to this distance. That is the standard deviation of the population. Then the standard deviation of this distribution, sampling distribution of all samples mean, this standard deviation will be smaller than the standard deviation of the population. How much smaller? Depend on my sample size. The standard deviation of the population will be divided by the square root of the sample size. Then the bigger is my sample size, the smaller will be this quantity. This distance will be divided by the square root of n. Then the standard deviation will be smaller. If the sample size is bigger, for example like this, when I compute the mean of this sample size, of this sample, the mean will be closer to the true mean of the population. If I compute the sample size of all of this sample when I increase the sample size of all of these samples, all of them are the same size, and I compute the mean and I plot all of these samples in a number line, the majority of the sample will be plotted close to the true mean of the population. When I finish plotting all samples in this number line according to the measurement of the samples mean of each sample, I will obtain a normal distribution. Because my sample size is bigger, then the standard deviation of the distribution will be smaller, then the distribution will be narrower. If this distance is the standard deviation when my sample size is n1, then this standard deviation will be smaller. If we increase the sample size, we can obtain other sample distribution narrower, even narrower. The bigger is the sample size, the narrower is the distribution, which is the limit. Then if we increase the sample size bigger and bigger and bigger, and we obtain all possible sample size of this size, and we compute the mean of all of these samples, actually we are going to obtain a distribution of all samples mean very close to the true mean. Could be this line, that is the limit. My sample size is 1 unit less, the mean of this sample will be the same of the mean of the population. Then all of these samples will be plotted one above the other following a vertical line. For big sample size, we obtain a normal distribution like this. The distribution of all sample mean will be like this. That is the idea of the central limit theorem. But we did this analysis assuming that the individual values follow a normal distribution. Here, points represent individual values, but in that distribution and in this distribution and in this distribution, points represent sample of size n. What happens if the population individual value are not normally distributed? If this population have a non-normal distribution like this for individual value, the distribution for samples mean taken from this population, if the sample size is small, the distribution will be ugly like this when my sample size is smaller than 30. However, when my sample size is bigger than 30, then the distribution doesn't matter how ugly is this distribution for individual value. The distribution for samples mean follow a normal distribution. That is a great discovery. In the same way, we can obtain the sampling distribution of any statistic. We can compute other statistics in all of these samples different to the mean. For example, the standard deviation, the variance, the mode, the median, whatever statistic, and we can analyze the sampling distribution of those statistics. For example, let's study the sampling distribution of sample proportion. Suppose that in this population we want to study one characteristic. This characteristic could be a qualitative characteristic like political affiliation, gender, religion, age, whatever. For example, if we want to know who will be the next president of the United States, we can compute the proportion in the population of all people that are willing to vote for this candidate. We need to count all people here, suppose that is X, and we need to divide X by the total population. If we want to predict who will be the next president before the election, we select a sample, and in this sample randomly selected, we compute the sample proportion. How can we compute that? We count all people that are willing to vote for the corresponding candidate and divide it by my sample size. But suppose that the proportion of people that are willing to vote for this candidate is 45%, and we are going to select a sample size 200. We are going to select only one sample to make a prediction. For that reason, we are interested in determining how is the distribution of the sample proportion. Let's select all possible sample size 200. All of the sample will have the same size, and let's compute the sample proportion for all of these samples. X2 divided by my sample size. Let's count all people here and divide it by the total. Let's compute the proportion for all of them. Let's study what is the variation of all of these results in this number line. This number line starts in 0% until 100%. And here we have the true proportion of the population, which is 45%. Suppose that for this sample the proportion was 50%. Let's plot this sample here, 50%. And we are going to do the same with the other samples. Let's compute the proportion. And when we obtain another sample, 0.50, we are going to plot this sample above this one. All samples located here have a proportion 0.50. All samples with the same proportion will be plotted one above the other. All samples that have a proportion equal 45% will be plotted here, one above the other. At the end, we are going to obtain this pile of points, which represent the sampling distribution of proportion. It is no surprise that this distribution is normal when my sample size is big enough. That is the distribution for all sample proportion of the same size taken from this population. In the center of this pile, we have the true proportion. Then the mean of all sample proportion will be the true proportion of the population, and the standard deviation of all sample proportion is given by this formula: a square root of the true proportion times the complement of the true proportion divided by my sample size. Remember, 3 standard deviation to the right of the mean and 3 standard deviation to the left of the mean must reach these 2 points between. We have approximately 99.7 of all samples values, sample proportion. And again, the standard deviation of the sample proportion depends on my sample size. The bigger is my sample size, the smaller will be the standard deviation. Remember, when we increase my sample size, the sample proportion will be closer and closer to the true proportion of the population. For example, if we increase these samples from 200 to 1000 and we compute the sample proportion in all of these samples, all sample proportion will be close to the true proportion of the population. If we want to plot all of these samples, sample size 1000 in this number line, we are going to obtain a normal distribution again, but the distribution will be narrower and the standard deviation will be smaller. We can change my sample size in order to obtain a sampling distribution closer and closer to 0.45 to 45%. We are going to use the sampling distribution of the statistic to make inference about the true parameter. Also, we are going to use this concept to test hypothesis about the true parameter.